So here's a little table that's from your book that summarizes the domains and ranges of all the trig functions. So I'd expect you to learn these eventually, and hopefully they'll just start coming with time as you work with these functions. So now let's look at the periodic functions, and we're going to use periodic functions to find the exact values of the trig functions. And a function f is called periodic if there's a positive number p such that whenever theta is in the domain of f, so is theta plus p, and the function's value at theta plus p equals the function's value at theta. So if this was theta and this was theta plus p, the idea is that you're getting the same height on the wave every time you go p farther along the axis. So let's think about how this applies to the trig functions, and let's think about sine of theta. And sine theta has the same value as the y-coordinate of the point on the unit circle. So we can find other angles that have the same y-coordinate as a given angle by going around the circle again. And every time we do that, we're going to get to another point that has the same y-coordinate. So the period is 2 pi. If we go from, say, pi over 4 and find the cosine of pi over 4, and then we find the cosine of pi over 4 plus 2 pi, those are going to be equal. So do you see how that fits this model? If I go to pi over 4 plus 2 pi, so p, the period, is 2 pi. So cosine theta also has a period of 2 pi. And here's a math shorthand way of expressing these periodic properties. It says that the sine of theta plus 2 pi k is going to be the same number as the sine of theta, and the cosine of theta plus 2 pi k is going to be cosine theta. So this just says that the period is 2 pi, so the first time it happens is after 2 pi, but then it keeps happening again every time you go another 2 pi around the circle. So the sine and cosine, and so then their reciprocals, of course, have periods of 2 pi. But notice the tangent and cotangent have shorter periods. Their period is pi. Because if I think about the tangent is this ratio of b over a, well, negative b over negative a is going to give me the same ratio. So the tangent and cotangent repeat more frequently. Every time you go pi farther around the circle, you get to an angle that has the same tangent and cotangent. So we're going to use the fact that the trig functions are periodic to find the exact values of these numbers, and that's the end of that objective. So then we're going to use even-odd properties to find exact values of trig functions. So just a little refresher from algebra about what does it mean to say even and odd. An even function says when you put negative theta into the function, you get the same value as you do if you put theta in. So one of the simplest functions that works like this is x squared, because if I put f of negative x, it says put negative x in there, oh, and I get the same thing. So if f of negative x equals f of x, remember we call this an even function, and it helps me to remember because an even exponent makes this happen. So then odd functions say if you put negative theta into the function, you get the opposite value than you had. So the simplest one of these, of course, is x cubed. So if we have f of negative x and we put negative x there and cube it, we'll get negative x cubed, which is the opposite of what we started with. So to summarize the trig functions, let's see, it looks like sine theta is odd. Let's see why this happens. If I go to theta, here's theta. And then if I go to negative theta, look how these have the same cosine. So theta and negative theta have the same cosine. So that's an even relationship. but they have the opposite number, whatever this number is, it's the opposite number down here for their signs, so that is an odd function. So we'll use even odd properties to find exact values of these trig expressions, and that's the end of this section.